Okay, so I'm going to be discussing how to make a reaction time strip and how to find the formulas or calculate the formulas and input them into Excel, and then how obtaining the data and analyzing the data. So the first thing is just the supplies that you need to build the strip and the shield. The strip, you're going to need large pieces of cardboard, preferably just over 1.5 meters in length. I prefer that over trying to glue small pieces together and be accurate with measuring multiple times. And then glue, 3 paint sticks is what I ended up using, clear packing tape, tape measure, box cutter style knife, and heavy weights such as heavy books or weights if you have them laying around. You go ahead and start by cutting 3 long strips of cardboard to a length of 104 millimeters and a width of 5 millimeters. That is because the Excel spreadsheet that you're going to end up making and cutting out, the distance between the cells is 5 millimeters, and there's 1,000 millimeters that you are measuring. And then there's a little bit of a header at the top. So that just gives enough length to be able to attach your entire spreadsheet once you've cut it out. And then a width of 5 millimeters. And you go ahead and start by applying glue generously to one long strip on one side. You go ahead and set the second strip of cardboard directly on top of it. Lay some heavy weights or books on top and allow it to dry for several hours. After the 2 pieces of cardboard are bonded together, then add another layer of glue and carefully lay the 3 paint sticks on top end to end. And then I go ahead and put glue on top of the paint sticks and put that third strip of cardboard directly on top, weigh it down with some books and weights, and let it dry for several hours until it's set. So there's a photo of one of the phases there drying, and I've got cardboard underneath so I don't get glue on my carpet, and paper bags on top so I didn't accidentally glue my school books to my strip. And here's a side view of the cardboard and paint sticks. You can see the 2 cardboard strips right there that are glued, and then the paint sticks on top. And then after the strips have dried and firmly set up, go ahead and take out the spreadsheets that were constructed and cut out, and I will go over that shortly here. I used a paper cutter. It made it easier to get it straight and then evenly cut. So you go ahead and line up the bottom of the column, which should be the lowest value, to be even. So you're starting at 0 at the bottom of the strip, and then to be even with the base of the cardboard strip, and then attach. I went ahead and used clear packing tape to attach. And actually, before I even attached the spreadsheets, I had wrapped the cardboard strip with white paper and packing tape just to try to make it look a little bit nicer. It didn't really work. And just protect it too from getting wet or getting damaged or anything like that. So then you go ahead and attach all the spreadsheet strips and tape it on there really well and as evenly as possible. And then to construct the shield, I grabbed a pretty big piece of cardboard, that was pretty long in length. So you just go ahead and start on one side of the cardboard. I went ahead and laid that RT strip down and cut along the top of the RT strip so that the length of the first length I was cutting was the exact length of the strip. I made the mistake of actually doing this RT shield twice because I didn't think about making sure it was going to be big enough to let my strip slide freely. And so the first one I made was too small. My strip wasn't falling out it was getting stuck. So I went ahead, the next time I was a little bit more careful. And I think the best thing is just to, cut that top, the first height at 12 millimeters. Then you want to measure up 50 millimeters. Go ahead and cut up 50 millimeters and then cut across again for 12 millimeters. And then the third cut, you want to cut up another 50 millimeters, cut across for 12. And I have a picture of that in my next slide. So here you can see my strip. It's flush. It's kind of hard to tell that it's flush, but the first length is the length of this strip. And then from that tier to the second one, it's up 50 millimeters. From the second to the third tier, it's up 50 millimeters. I also scored the cardboard a little bit. You can kind of see, you got to be careful not to cut all the way through, but it just makes folding it, because you are going to fold it into a triangle, makes that a lot easier. So that's what I did next. Went ahead and folded it. You can see me holding it at the D equals 100 spot there, and then go ahead and tape it firmly, and it's this nice little triangle shape. So then the Excel part, and actually I'm kind of going out of order. I was constructing the strip and then also working on Excel as well. And that for me was probably the biggest challenge. Excel is a little bit challenging for me at least, but you go ahead and calculate the first equation for the RT strip, which that's where there is no velocity. The strip is coming out flush with the base of the shield, and so the initial velocity is 0. Use kinematic equation 2 to solve for t, which is delta y equals 1/2 AYT squared, and delta y is the downward displacement of the RT strip. When the subject catches it, t is the subject's reaction time. So for that to solve for t, it's square root 2 times delta y over g. And this is the equation that needs to go into Excel for the first set of values when there's 0 initial velocity and when the RT strip starts at the base of the shield. So here's Excel, and that's how the formula has to actually be inputted. And that for me was probably one of the biggest challenges, was figuring that out. So you do an equal sign, and then you have to type square root 2,000 times A5, which is the column, and that's the change in y, basically, all over 9.8. And there it is. And then you can go ahead and this will light up flashing the column that you want to go ahead and click and drag all the way down. Or if you're like me that couldn't kept messing that up, you can actually put in A5 and then colon to the length, to the last column, like let's say it's 200. So that was for the first strip. And so that's one side of the RT strip is going to be the D equals 0, and it has the time in milliseconds and then also the distance. And then for the next two values on the strip, where it's had some velocity because it's fallen a certain distance before it even comes out of the shield, you have to calculate the initial velocity as the strip is leaving the shield, which is going to be different, obviously, in the first equation and between these two equations. And that's done starting with using kinematic equation number 2. So you end up with the initial velocity. For example, this is for the 50 millimeter or 0.05 meter drop. It ends up being square root 2 times 9.8 meters per second times 0.05, which gives you 0.99 meters per second. And then you go ahead and put this into kinematic equation number 3 to solve for t, and you end up using the quadratic equation to do that. And that equation 3 is Vy final squared equals Vy naught squared plus 2Ay delta y. And then to rearrange that, it's delta y over g divided by 2t squared plus Vy naught t. And so you end up with 9.8 meters per second squared over 2,000 t squared plus 0.99. And then you have to solve using the quadratic equation. So that's how I have it set up here. T equals negative 0.99 meters per second plus or minus, and then the 1 in front of the square root, 0.99 meters per second squared minus 4 times 9.8 over 2,000 times negative delta y. It's negative because it's going downward, and that will work out mathematically because we're going to end up with a positive number under the square root, all divided by 2 times 9.8 over 2,000. And the also important to note, there's a plus or minus in the quadratic equation. We're only going to end up taking the positive value because we're talking about time and we're moving forward in time. We're not going in negative time. So that you'll see as I kind of continue through with the equation. So here's the formula, and here's what's going to ultimately go into Excel for the t at 50 and the t at 100. With the initial velocity coming out at 50 millimeters and coming out at 100 millimeters. And here it is in Excel. This is a screenshot of it with it at 50. And then here's the formula. I just went ahead and wrote it below for what it would be for 100 millimeters. And so you plug that in, get your set of values, and that's what you're going to end up cutting out for your RT strip. And then after building the RT strip and getting, the Excel form, then it's time to go gather some data. So I went ahead and tested 3 different subjects. The RT strip was dropped 10 times per right hand, 10 times per left hand with a D equals 0, D equals 50 millimeters, and D equals 100 millimeters. They were asked to wear headphones with music so they couldn't hear the cardboard sliding out and kind of preemptively be ready to grab it. And I then recorded where they caught the RT strip, or I guess I should say the time that they caught it, and then plugged that into Excel and got the mean and standard deviation, which Excel helped me calculate. So subject one, they had, here's all their data, it includes their data for their right hand, left hand, D equals 0, right hand, left hand, D equals 50, right hand, left hand, D equals 100. And then below the data points, the first line is their means, and then the second line is standard deviation. Same with subject 2 and subject 3. And then the ratios of the means of their right to left hands, and to know all three subjects were right-handed, were for subject 1, the ratios between right to left was 0.837 at D equals 0, and then at D equals 50 it was 0.767, and D equals 100 is 0.823. Same with not same with subject 2, but subject 2, it was 0.980, and then at D equals 50 it was 0.949, D equals 100 is 0.891. Subject 3 was also kind of in the mid to high 80s, 90s area between those ratios. And the average differences between the right hand left catches for the all three distances for all three subjects, and I should clarify, this is the average differences as far as their standard deviations, was for subject 1 0.809, subject 2 is 0.94, and subject 3 is 0.899. So what does this mean exactly? In all three subjects, they had a faster reaction time in catching the RT strip with their more dominant right hand, which I would have predicted. However, the difference between the right and left hand means was not that big, especially between two of the subjects. And this is what I would expect, that the reaction times would be faster with the more dominant hand, but not by a great number. And so to kind of break down the three different subjects and their data, subject 1 had the fastest average reaction times with the first two distances of D equals 0, D equals 50. And the faster the reaction times, the more accurate they are, is kind of what I concluded. And this is because distance travel depends on time squared. So with every increment of time that goes by, there are longer and longer gaps in the distances. And with longer gaps in distance, measuring accurately becomes more and more difficult. So it'd be like measuring something in inches versus millimeters. The measuring device with smallest increments will provide more accurate measurements. And then also with subject 1, I made a note here, they had the largest average standard deviation. So they have the fastest reaction times on average with at least two of the distances, but they weren't necessarily as consistent with themselves, if that makes sense. Their average standard deviation of all three measurements was 32.3. So they had a pretty big spread between in just their catches within even just using their right and their left hand. Their right hand, they were a little bit more all over the board than the other two subjects. And as far as how accurate they were between their right and left hands, for subject 1 at D equals 0, there was a difference of 29.0 with their mean reaction times between their right and left hands, their right being more dominant and faster, and that's true of everyone. And then at D equals 50, there was a 38.7 difference between their means on their right and left hands. And D equals 100, there was a 34.1 difference between their means on their right and left hands. So as far as like between their right and left hands, they had the biggest difference with their catches out of everyone. Subject 2 had the second fastest average reaction times with D equals 0 and D equals 50. At D equals 100, they had the fastest average reaction time. Their average standard deviation spread out between all the measurements was 25.3, and subject 1, I think it was 30 something. I'd have to go back to that slide. I want to say it was 34, something like that. Subject 2 had the most accuracy of all three subjects between their right and left hands. The mean between the right versus left hand for D equals 0 was only 4. For D equals 50 millimeters, it was 8.8, and D equals 100, it was 16. So they had the best accuracy between their right and left hands, especially at the slower velocity times. Subject 3 had the slowest average reaction times at all three distances. Their average standard deviation, though, was the lowest, but not by much. It was 25.0, where I think subject 2 is 25.3. So they were just a little bit more consistent with themselves as far as all their catches were closer together on average than anyone else, and quite a bit than subject 3. And then as far as between the right and left hand differences, at d equals 0, it was 13.6. D equals 50 is 22.1, and D equals 100 is 23.0. So they were not as accurate between their two hands as subject 2, but more than subject 1 by quite a bit. So it was kind of interesting. Subject 1 had the fastest average times, but the biggest spread as far as their consistency with catches and the biggest discrepancy between their left and right hands. So that I'm not sure what to make of that, but that was a little interesting. So the pros and cons of a 250 millimeter RT strip, I kind of had to think about this for a bit. And as far as cons, I think it's not quite as accurate because, like I mentioned earlier, the distance traveled depends on time squared. So every increment in time means larger gaps in distance. So dropping 250 millimeters up, it's going to have a lot of velocity. More time is going to pass potentially. And because of that, there's probably going to be larger gaps in distance. And so it's a little bit harder to measure reaction times as finitely, is that a word? As accurately, as closely. Pros, I had a hard time coming up with pros, but I guess it'd be another set of data points to obtain reaction time and just to kind of compare with the other data you have. And yeah, it'd be kind of interesting to see, I guess. Like, I wonder if subject 1 would still have the fastest reaction time with that strip coming out at a much higher velocity or not because they, had the bigger discrepancies. And would the discrepancies between the right and left hand be even greater with a faster traveling strip? I don't know. So that would be kind of interesting to check out. So that is all. I hope you enjoyed. Thank you very much. And that is the end.